So computers are ideal for computing integrals. In fact, you have access to one if you have internet access at wolframalpha.com. So let's just have a look. So here we're going to, as the example illustrates, we're going to look at that example where we had the x squared and then the x cubed plus 5 to the 9th as the integrand. So let's just see what Wolfram Alpha does. Okay, so here we've typed in our command integrate, and then here's the integrand. By default, Wolfram Alpha will assume, since x is the only variable in the equation that, or the expression, that it'll integrate with respect to x. And so we see it goes ahead and it returns a solution. Kind of a big solution. In fact, what it's essentially done is expanded out that thing that we gave as an answer, but we can ask it to show steps. And we can see that in the steps, for the integrand, make a substitution. So it's telling us, make a substitution, u is equal to that, and therefore the differential du is 3x squared. And then it goes through exactly the steps that we did. It got the same answer as us, and then it gave this equivalent form and expanded it all out. So computers, computer algebra systems, for the most part, have the ability to compute these integrals. It's best that we be warned that you still need to understand how to do these computations yourself. For one, Wolfram Alpha won't be around during assessments, but also the point of this course is to learn the techniques behind integration, because as we'll see later on, that we can find very simple integrals, very simple in the sense that just created from our elementary functions that we have, that Wolfram Alpha won't be able to answer. And the other computer algebra systems won't be able to answer either. They seem to choke on them. But we can do them by hand rather easily just by using the techniques that we're going to learn, substitution, etc. So be warned, you can use Wolfram Alpha to help you with understanding the material, but you, in essence, need to be able to do this stuff yourself. Okay, so now let's look at the definite integral and see how we can use substitution to answer questions regarding definite integrals. If g prime, so the derivative of g is continuous on AB and f is continuous on the range, then that's, again, just conditions to make sure the integrals we're talking about exist. The meat of this argument is really right here, or this theorem is really right here, that the integral from a to b of f of g of x times g prime of x dx can be obtained through a substitution, so by putting everything in terms of u. And the thing to keep in mind is that when you put an integral back in terms of u, you need to put the limits of integration, which are originally limits in terms of the variable x, you need to put those things in terms of the new variable u. So our limits of integration must change as well based on the new variable we're using. Okay? So be warned that when you do an integral like this, a very common mistake is to do the substitution and to write the new integral, but forget to change the limits of integration, and then in the next step change them. The problem with doing this is this intermediate step here is not correct anymore. This integral is not equal to this integral, because this integral, the values that x takes on are between a and b, and in this integral, the way we're reading it is the values u takes on are between a and b, but that's not the case. Those are the original values of x. The values of u should be between g of a and g of b. So don't put that intermediate step in. If you're going to change the variable, change the limits of integration as well. So let's look at a couple of examples. In this first example, we're looking at the integral from pi to 2 pi of cos of 3t dt. Here we're just guided by the fact that we know how to integrate the cosine function if the argument is just a variable. Here we've got this extra factor of a 3 in there, so let's substitute for it. U is equal to 3t, so du is equal to 3 dt. And we can also change the limits of integration as well. And here, our old limits of integration were in terms of t. So the old limits of integration were t equals 2 pi was the upper limit, t equals pi was the lower limit. Let's figure out what those things are in terms of u. Well, if u is 3 times t, then when t is 2 pi, u is 6 pi. And when t is pi, u is 3 pi. So our new integral becomes the integral from 3 pi to 6 pi of cos of u, and then notice that the dt is now 1/3 du, so we got this 1/3 out front du. And so there's our new integral. Our original integral with these limits of integration is equivalent to this integral with these limits of integration, and this one's slightly easier to work out. The antiderivative of cosine is sine of u, and that goes from 3 pi to 6 pi. Sine of 6 pi, sine of 3 pi, both of those are 0, so the result here is 0. In this next example, we've got the integral from e to e squared of ln of u squared du all over u. And again, we'd like to try to substitute for something. Try to scan through the integrand, see if there's a piece in there where the derivative also appears. And the piece here, which is the logarithm, w equals ln of u, its derivative also appears. That's du over u. The limits of integration change as well. The original ones where u is e squared and u is e. And those become w equals ln of e squared, which is 2, and w, which is ln of e, which is 1. So our new limits of integration are from 1 to 2 of 1 over, let's see, what is this? ln of u squared, so ln is now w, so this is w squared. Du over u becomes just dw. So this integral is equivalent to the integral from 1 to 2 of w squared dw. And that's something we know how to work out. Also notice what this is really saying. It's saying if we look at this function, the function ln of u squared all over u squared, and we plot it, let's say y is equal to this thing, so we plot it on the uy axes, our coordinate system, and we look at the integral as representing the area under the curve. In this case, it's going to be an area because this integrand is positive on the integral from e to e squared. So we're looking at the area under that curve. We may not be able to imagine what the curve looks like. We may need to do some sort of curve sketching techniques to get an idea. But regardless of what it actually looks like, what this is saying is that the integral under this curve over this interval, the area of that region, is equal to the area under the region of the parabola from 1 to 2. So this is a statement about areas under curves being equal. And so if I want to know what the area under this curve is on this interval, in other words, what this integral is, we've just now established that, well, it's the same as the area under the parabola, w squared, over this interval. And that's easy to work out. That's 1/3 w cubed from 1 to 2, which is 8/3 minus 1/3, or 7/3. And so the area under our parabola from 1 to 2 is exactly the area under this curve from e to e squared, and so we got our answer. The goal here was to use substitution to take a complicated integral and convert it to a simpler one that we knew how to work with. That's the general rule of problem solving. Take a problem you don't understand or you don't know how to deal with, or that seems difficult, and convert it to one you do know how to deal with or you do understand. In this case, it was converting this complicated integral to a simpler integral through the technique of substitution. Okay, in this last topic, I just want to mention some properties of even and odd functions. So just recall that an odd function was a function that had symmetry about the origin, and an even function was a function that had symmetry about the y-axis. So here's two typical examples, or maybe classical examples of odd and even functions. The function, in this case, this is y equals x cubed, and in this case, this would be like the function y equals x squared. Okay, so the statements here, if f is odd, then the integral over a symmetric region about the origin, or a symmetric interval about the origin, has to be 0. Why would that be the case? Well, let's look. Suppose that was negative a, and then therefore over here is a. What does the integral represent? Well, the integral represents the signed area. So it represents this area minus this area. But due to the symmetry, these areas, so as positive quantities here, these areas are equal. So when I look at the signed area, or the integral, they'll cancel out to give us 0. On the other hand, if our function is even, then the integral represents the area of these shaded regions. And since the regions have the same area, due to the symmetry of the evenness of the function, then the integral is exactly twice the integral of only one of the pieces. So noticing whether the function is even or odd can sometimes allow us to simplify the integrals that we need to compute. So let's look at this example. We're looking at the integral from negative 3 to 3 of 2x to the 4th plus the 3x squared plus 4. Notice here that this is an even function. All the powers of x are even powers, and it's an even function. It's got symmetry about the y-axis. How can you check that the function is even? We just need to check that if I plug in negative x into the function, I get the same value as plugging x in. And so you can check this. Check that this is the case. Check that when you plug negative x in, you get the same value as plugging x in. And that tells you that it's got even symmetry about the y-axis. Okay, so what does it mean if it's an even function? It means that if we integrate it over a symmetric interval, I really only need to consider half of it and multiply the result by 2, because the other half is just the same value. And so this tells me that I just need to look at integrating from 0 to 3 and multiply by 2. And so this is then 2, the integral of this would then be 2/5 x to the 5 plus x cubed plus 4x from 0 to 3. And at this point it's nice to notice that there was symmetry here, because I'm going to eventually have to plug in the upper and lower limit of integration into the expression. But since one of the limits is 0, I effectively can ignore it, because when I plug it in, everything just becomes 0 anyway. So this is 2/5 3 to the 5th plus 3 cubed plus 4 times 3, which is 1,362 over 5. How about this next one? Okay, so this looks like a complicated integral. I've got exponentials and signs, and there's a quotient here. We're integrating over a symmetric interval about the origin from negative e to e. Notice that this is an even function. This is an even function. But that one's an odd one. And so the product of an even and an odd function is an odd function. And the quotient of an odd function with an even function is an odd function. So in this example, our integrand is odd. And so if we integrate an odd function over a symmetric interval, what's the answer have to be? Yeah, it's 0. Because whatever the function looks like, it's sort of got to do the opposite over there. So these regions will cancel each other out. And so our result is 0. And that's it for this section. Thank you very much for watching.